So today I want to start with sorting. And there are simple sorting algorithms and complex ones. We're just going to look at the simple ones. We'll just look at one simple one, actually. And if you need to sort a large list, then the simple algorithms are not very efficient. And so you would want to use one of the more complex ones. So I'll show you a sorting algorithm called selection sort. And that's what I'll do. And just to keep an eye on these assignments, there's a problem to implement linear search, binary search, and sorting. So here we have a function called mySort that gets an array of int of size len, and it rearranges the elements in A so that they're in ascending order. We could also do descending order as well, but we'll do ascending order in this case. And then there's, we want to compare our result, compare our implementation of sort with the sorting routine that's available in the C++ standard library. And that sorting routine is more efficient. That'll be a lot faster. So we're going to examine the difference in time there. And we'll examine it experimentally. And maybe talk a little bit about it theoretically. So in sorting, well, let's just see we have this, our hello program working first. All right, that's good. So the idea of sorting here is we take an array of values so there's 5 values there. Let's go a little farther. Let's go 7 values. And so we have this array. And we want to call the sort routine. We're calling it mySort because the routine in the standard library is just called sort. So we don't want a name conflict. So although we can avoid that because it's in a different namespace. So I'll do it this way anyway. So mySort A, and then the size of A, which is 7. So we sort it. There's 7 elements in A. And after sorting, we want to check that things are in the right order. So we want to check that A of 0 equals -2. We'll go down the line. We've got A of 1, 2, 3, 4, 5, 6. That's 7 elements. The first element after sorting should be -2. And then 0. And then 1. And then 3. 4. 5. And 9. So this test should fail. mySort was not declared. So Let's declare mySort. It doesn't return anything. It modifies the contents of the array A that's passed into it. That compiles, and we have the assertion fails. Now, why does it fail on this one? It should fail on that one. You see, there's a problem with the test code. Why doesn't it fail on the first one, but it fails on the second one? You won't see this issue come up in other languages, I want to tell you. Well, no, it might, actually. It might. No, it won't. In another language, it'll say, in line 15, it won't compile in another language, say maybe Java, C#. It'll say something like, the argument passed into assert is not a Boolean value. It'll fail to compile. But in C++, it doesn't check for that. It just compiles it. Anybody see the issue? Why does it fail? Why does it pass on the first one and fail on the second one? So we have an array A. These are the elements. A of 0 is 4. That's not -2, is it? So it should fail, but it doesn't. 15 succeeds. Assert thinks it's getting a true value.
Is it because you're using single equals signs? Are you assigning a value?
Exactly. There's a single equal sign, so I'm doing assignment. So look at what I've highlighted right there. That assigns -2. This modifies the array A. It assigns -2 into position 0. So the 4 is overridden by -2. Now, after that assignment operation completes, that we have an expression there, see? What does that expression evaluate to? It evaluates to -2. Let me test that, okay? I'm going to test that just to make sure I'm doing that right. So this expression evaluates to -2. So I'm going to print that out. And it's just going to return here. I don't know if it'll compile. What is going on? Invalid operands of type int. Oh. Is that right? Invalid operands of type int. So we run this. We get -2. So this expression here evaluates to -2. So the expression does two things. It evaluates to -2. It's replaced by -2. It also causes the assignment of -2 into position 0 of A. So this evaluates to -2. So why does line 15 not fail? It's line 16 that fails. Anybody know why? I'm going slow because I want to nail this in so you remember it. Well, in C and C++, those languages, the integers are bools and integers are kind of interchangeable. So an integer can be used as a bool. So -2 is treated as a Boolean value. And apparently -2 is treated as true.
Is it because when it's doing it, it's reading what you wrote as a of 0 is equal to 2 as the first one, so then a of 1 should be 3?
One more time.
Is it reading it that because you said a of 0 equal to -2, that the next number a of 1 should equal 3 because that's the next one in the array?
So you're saying a of 1 would become 3?
Is it reading it like that because you said it equal to -2, it starts the array at -2, so it's reading it like that? Or?
What do you mean it's reading it? This expression that I have highlighted here evaluates to -2. We're not talking about the array anymore. We're passing -2 into assert. What does assert do with -2?
Checks if it's true.
Yeah, what does it say? What does it conclude?
That a of 0 is equal to
No. Assert doesn't see that. Assert, we're just thinking, we're passing -2 to assert. What does assert do with -2?
puts it in the function.
It treats it as true. Assert treats -2 as true. That's why we don't have a failed assertion. So that expression, a of 0 assigned to -2, that expression assert considers to be true. It evaluates to true. Because it evaluates to -2. But integers are used as Booleans. They're considered true and false. So the integer, so -2 is treated as true. But look at the next line. What does this evaluate to? What does that expression evaluate to? Yeah, you said it right back here. 0, right? But this expression fails. A of 1 equals 0, right? That fails. So that is being treated as false, because assert will terminate when you pass false into it, or an expression that evaluates to false. When you give assert an expression that evaluates to false, it will terminate the program with an error message. See that? So Boolean 0 is treated as false. All other integers are true. -2 is true, 1 is true, 9 is true, 1,000,000 is true. The only integer value that's considered false is 0.
Is that like a binary thing almost? Because is that how Booleans
Well,
work? Like it's either 0 or something else?
Well, I'll explain why they did that. Because, when you have, well, I don't know exactly why they did it like that. I would say that, the AND operation, you say A and B. Well, that's similar to multiplication, so A times B. So if you use integers to represent bools in the way that we're talking, if you have a 0, if A is 0, then A times B, it doesn't matter what B is, the whole expression will be false. So it wants to, I think the idea there is to preserve the AND relation. They want to map the AND relation onto multiplication and have the same result. But I don't think it works with OR. Because if you had, -1 and 1, right, those are both true. So if you said -1 or 1. Well, if you added them together, you'd get a 0, which would be false. So you can't go true or true is false. And so it doesn't work with the or operator, but with the and operator works as if it was some multiplication. And it could be something to do with hardware, the way the hardware works. I don't know why they sort of did that, but I don't know the rationale. Do you see the bug there? So how do we fix this? Well, it's just we got the wrong. We don't want assignment, right? That was a mistake. It's a coding mistake. No, it's wrong.
You didn't sort it.
Yeah, we didn't sort it. We just have a stub. But now we got the behavior that we expect, right? Well, we knew we were going to get a failed assertion. Well, we didn't know it would happen in line 16. So when we saw that, we slowed up and said, "What's going on? Something's wrong." So we got the bug out. We got the bugs out of the test code. All right, so that's just a warning to you that you gotta be careful with the test code. What about sorting now? Let's go ahead and sort this. So basically what we're going to do is this. I'll show you in a comment here. So what we're going to do is take a variable I, and we're going to point it at the first position. And we're going to say, all right, I want to put the smallest number there. So I need to look at this, then this, then this, then this, and I want to find the smallest number. So I'm going to scan across here with J. So I'm going to say, I'll look at J equals 1. So J is pointing at 9. You know, is 9 smaller than, is the thing at J smaller than the thing at I? No. Is the thing at J smaller than the thing at I? Yes, it is. Oh, okay. So now we're going to swap those two. We're going to swap -2 and 4. See that? So we found a number that was smaller. J is scanning across all these elements. When we find a number that's smaller than the number at I, we're going to swap them. So 4 and -2 have been swapped. And then we continue down the list, but nothing else is smaller than -2. Now -2 is at I. We don't find anything. And what do we do when we get to the end of the list? When we get to the end, it means that position 0 is taken care of. So then we're going to increment I, so now it points to position 1. And then we're going to reset J so that J is, oops. We want J to be 1 past I. And then we're going to say, oh, by the way, this is the old list. Okay, I'm going to take it out of here. That's the old list. So now I is pointing to this. See, everything to the left of I is already sorted. -2 is sorted. That's the smallest thing. Now we don't want to find the next smallest thing. So we let I point to the next space. So we need to fill in this slot 1. So we let J range to the right. We're looking for a value that's smaller than 9. Oh, but 4 is smaller than 9. So we're going to swap. We're going to swap 4 and 9. You know, this is the result. This is the initial array. This is the initial array. This is the result when we fill in the first position. So I is pointing to 9, J is pointing to 4. We're going to swap those two. 9 goes there, 4 goes here. And then we keep scanning to the right. j goes to the next value. Oh, 3 is smaller than 4. Let's swap those two. You see, we keep searching for a smaller number. We want the number that's at I to be the smallest that we find. We're going to keep going there. J is now 1. Well, 1 is less than 3. Let's swap with 3. Let's keep going. J is 0. 0 is less than 1. So let's go ahead and swap like that. And then finally, J is 5. Well, 5 is not less than 0. And so this is all set. We're good there. See? So this was the next iteration of the outer loop. I'll just keep recording that. See? So in the beginning, nothing is sorted. And then as we go along, we get more and more done. So now what do? Now these two values, -2 and 0, those are the smallest values in the array, and they're in the right order. So that's good. Let's going to advance I to the next value. Now it's at 9. I'm going to reset J. So J comes back to 1 past I. Now we're going to be looking at this 9 here. 4 is less than 9, so we're going to swap with that. Advance J. Now 3 is less than 4. We're going to swap with that. And then J is now at 1. 1 is less than 3, so we're going to swap with 3. 5 is not less than 1, so we're finished here. You see now we've got more and more of the loop, more and more of the array is sorted. And now we have these 3 numbers in the right order. Here they are. Maybe that's hard to read. These are all in the right order. So what we do is we advance I, because we want to go to the next position, that one, and reset J to I plus 1, 1 past I. Start all over again. 4 is less than 9, so we'll swap. Advance the J. 3 is less than 4, we're going to swap. Advance the J. 5 is not less than 3, we're done. I'm going to get rid of this. This is not useful. So what we have is all of these values, all the way up to I and including I now, is in the sorted order. You see that, -2, 0, 1, 3, that's in the right order. 9, 4, and 5, everything to the right of I we still have to clean up. Everything to the left of I is done. Everything to the left, at I and to the left of I is now in their final position. So we advance I and reset J to 1 past I. Compare the values at I and J. The value at J is less than the value at I, so we swap. Advance J. The value at J is bigger than the value at I, so we do not swap. So we're done. Then we increment I. J is going to be reset, but it doesn't move. It stays in the same position now. We compare the values at I and J. J is less than I, so we swap. See that? So now it's in sorted order, but when do we terminate? What's the condition? Well, J is at the end, so we advance I. Oh, but when I is at the end, we don't do anything else. There's nothing, the value at I is not, there's nothing after I, so there's nothing to swap what's at I with, right? So there's nothing for 9, no candidates to swap with 9. So you see that process? That's a simple sort algorithm. I think it's called selection sort. I think that's what I called it. What they call it, they. us. And see how that works? So we just have to code that up. Do you want me to show you how to code that up? Or do you want to try to do it on your own? What do you want to do? Does anyone want to try to do that on live, on camera? Anyone check this out? I forgot your name. I'm trying to remember. It's not Dustin. It's. I always confuse you guys. Is it Justin? Are you Justin?
No, Sharon.
Huh?
Sharon.
Oh, Sharon. Oh, and you're Dustin. You're Sharon?
Yeah, I'm Dustin. You're Sharon.
Oh, Dustin. Okay. Dustin, you want to do it? Do you think you can do it?
He wanted to do it on his own.
Oh, you want to do it on your own?
Or well, he wants to do it. I can try.
You want to try it? All right.
Oh, wrong person.
All right, let's see. Let's do it. Where are you in the list here? Oh, under it's alphabetical, isn't it? All right. Yeah, pull up a file.
It's under class example. Example 2.
This one?
One below. Class EX.
Oh, down there?
No, class EX.
Oh, it's in there?
Yeah. And then example.
This one right there?
Exactly. The bottom.
2? Yeah. Okay. All right. Yeah, that's good. You got the outer loop. Now see, this is going to range, I is going to range across there, right? It's going to go, I is the slow moving index, and J is the fast one. So J, every time you step I forward once, J is going to run to the end, and then, see? And then you step I forward one more time, and then J is going to run to the end. So every time you step I forward once, then J is going to sort of run from I plus 1 to the end. So that will be the inner loop. So J is controlled by the inner loop. Remember, we don't start at 0 though, remember? Remember, we started at 1 past I. Well, 1 past I, not 1.
So,
Just 1 after I. 1 more than I. That's it. Got it. That's it. That's it. You have the 2 loops right there. Those loops that you wrote right there control I and J just as we have described it. Except maybe the outer loop, you know, the one that's in line 8. We quit when I gets to the last spot. See? So yeah, so we don't, so when I gets to length minus 1, we can quit. You know, this code, as you wrote it right now, is okay. But if you go length minus 1, you're quitting a little. I don't know if it matters. It doesn't really matter, to tell you the truth, okay? You could do minus 1 or not. I mean, if you analyze it, you'll see that it's going to quit anyway. All right, so what do we do when we have a pair? See, here in this inner position inside the nested loop, you've got a pair I and J. And you know what? I is pointing to something that you want put the next smallest value into. And j is like running across from I out to the end. So at this point in time, right now, in line 10, you've got some I and some j. What do you do? Oh, I want to tell you swapping. Remember we were doing swapping? Oh yeah, no, that's good. To finish what you got there, that's good. So if the value at I is less than the value at j, then we can call this function swap. We can just type it in there, swap. And a parenthesis, and a of I, comma, a of j. Yeah, with a comma in there because it's a function call. This is a built-in function, swap, okay? And that's good. Yeah, you don't need that. You don't need that. Yeah, but you need a closing brace and a semicolon too. Yeah, that makes it easier to look at. Yeah, semicolon, that's good. And you close off the if statement with that brace. I mean, that's it. You did it. Think how simple that was.
Do you need to use the swap function, or could you just change that to, if that condition is true, can we just do a of I equals a?
Let me show you, I'll show you how to implement the swap function, okay? So we can use code. See, to swap what's in I and j, think of it like this. You've got two glasses. You've got a glass of milk and a glass of juice. And I want the milk to be in the other glass, and I want the glass of the juice to be in another glass of the milk, right? So you can't do it with two glasses. You got to have a third glass. So you need a third variable, a temporary variable to put one of them into until you. So we could look at that. Let's test this. So I'll test it. Assertion failed. We did something wrong. What is going on? So that's amazing. To me, it looks right, Oh. No, it didn't look right from the beginning. And I said, oh, I'll let, Dustin figure it out, or someone else. But you didn't catch it. And then I forgot all about it. Now we got a failed assertion, which is excellent, right? This is better than if you typed it in right. So what's the bug?
I need to call the swap function. Do I need to call the swap function with an include, or no?
So the swap function, what's the thing about the swap function?
Do I need to call it like I would call asserts on the top?
No, you're calling the swap function correctly. That is swapping the values at I and j. Can anybody debunk this? There's a logic error. I cannot give you the answer. You got to come up with this. Can you read through the code again? And reason about it. Look at it again. Just check it. I think I and j, they're ranging nicely. Okay, I got to tell you. your control of I and j looks very good. Okay.
Oh, shouldn't it be if A of I is greater than A of j, you swap them?
Yeah. Does that sound right?
Yeah.
Because if A of I is already smaller than A of j, that's good, right? Because A of I has got to get the smaller number. So you only have a problem. You only need to swap if the thing at j is smaller than the thing in I. All right, so now we're going to try this again. Good. It doesn't say all tests passed, but you know this is good. It doesn't have to.
If we switch that back to a less than, is that all you need to do to sort it in descending order?
Yeah, it is. It is. And let's test that, okay? That's the code we have now. That looks good. Now, if we want to go into descending order, these values have to be reversed. So this will be 9. This will be 5. This will be 3. 1.
Oh, it should be 4 after 5, right?
Oh, 4. Thank you. 4, 3, 1, 0, minus 2. Did that from memory. And now this will fail because we didn't change the inequality, okay? So 9 does not get into the first slot. We're still putting minus 2 in the first slot. But if we change this, we only swap when A of j is bigger than A of I. That means we're going to push all the big things to the front. So this will, I would bet, you know, I'd bet $10, 10 to 1 odds. You know, I would put up $10 against your $1 that this is going to say all tests passed. Ha! Got it. There, we got it. We were just playing virtual money, right? That's not illegal to do that with virtual money, is it? Okay. So that's it. That's sorting. And there's different ways. There's also other ways to sort. And I mean, you can read about that. If I just stand up here and talk about it, I don't think you're going to get much out of it. But what I can do is look at this with you together, this comparison here. So what I said was, you know, what we have is a slow sort routine. This is a slow sort routine. I'm going to set this back to make it ascending. And there's another way to do this. Let me do it like this. I'm going to copy main.cpp to slow.cpp. And we're going to open that up. Now we're going to create an array, A. Of size 100,000. 100,000 items. And now we're going to go into a loop here. I'll just copy it from up there. We're going to fill in the array. With the random numbers. Well, it'll be the same random numbers. So we're gonna code this as you know, we're gonna pass in 100 as the seed. or a 0. Let's say a 0. We get the same sequence each time. Maybe that's hard for you to see, so I'll do this. So we declared this array of 100,000 values. We better do it like this. Const int len equals 100,000. I think I need this const there. I'm not sure. Let's see. Oh, this shouldn't be -1. We got to go to the end. And then we're going to sort A, so size len. And we know it already sorts correctly, so we don't have to test that. I'm just going to say done. We're not testing that our algorithm works with a larger number of numbers. We based on our test with a small number of numbers, we think that it'll work with a larger number. Okay, so we're just going to go with that assumption, and we just want to see how the routine behaves when we have a large number. How much work does it do? Let's take a look. And I need to open up. Let me figure out how to do that. Oh, here. I'll just put it down here. All right, I need a header file. What is it? C standard live. That's a rand function. So we're going to run this thing. 1, 1,000, 2, 1,000, 3, 1,000. So we're counting here. All right, it's going to take a while. It's 100,000. Random values. Maybe we should try 10,000. $100,000. That's too much for us to wait for. Okay, let's bump it down to 10,000. 10,000. No, that's pretty fast, right? Maybe that's too fast. Let's bring it up to 30,000. It's a little slower, see that? Not too bad, right? Not too bad. Bring it up to 50,000. $50,000 takes a few seconds. Not too bad, okay? That's our test code. Now, let's look at a fast algorithm. So this is the other file called fast. We're not going to use mySort. We're going to use another header file called algorithm. It's got some algorithms in there. We're going to have the same test code. We're going to build the array in the same way, the same values, because we have the same seed 0. So we get the same sequence of values. And then we're going to call the sort routine. That's how you call it. This is the address of the first element. This is the address of one past the last element. That's how you call this sort routine. The first argument is the is the RAM address, the byte address in memory of the first value. And the second argument of sort is the byte address that's one past the last integer in the array. Now let me just check that I did that right. I did. See, I'd call it like that. I'm asking for 200,000 here. Maybe that's too big, right? That's too big for you. So the idea is just to pick a big number. So now let's compile that and run that. Look at that. Just in a blink of an eye, it finished. But remember how slow this is the same code, right? It's the same sequence. And look how slow the slow one is. So that the algorithm that we looked at is significantly slower. Look at that. And, you know, with slow, if we bumped it up to 100,000, remember we waited, I don't know, at least a half a minute. What happens if we bump the fast algorithm up to 100,000? Think it's going to get slow on us? And not the slow one, the faster. This is the one that we had to kill it, right? We had to kill this one with 100,000. But with the fast algorithm, watch this. I'm going to drop my hand when I hit the enter key. You see that? My gosh. In fact, this thing can get gigantic. And it's just going to finish. Look at that. Actually, you could put the max int in there. I think they call it int max. Int max. Let's see if that's the largest possible integer. What is int max? Int max. I think it's called int max. Is that in limits? Is it C limits? Yeah. Ready? This is the maximum integer. Oh, segmentation fault. It's too big. Sorry about that. The memory can't hold it. So, how about int max divided by 2? Still too big. Anyway, the story is it can get really big, and it's still going to work. And what's going on there? Well, this fast algorithm that's built into the C++ standard library, if the size of the array is n, then the speed, the time it takes to finish the sort equals some constant times n, the size of the array, times the log of n. That's the formula that estimates the time that the sort routine is going to take to complete. See, that's the fast one. That's the one that we don't know how to do. But the slow one, the slow algorithm, the one that we know how to do, the one that we did with the swapping and the nested loops, the time it takes is some constant. Let's look at the algorithm. See, this loop here runs n times, roughly, okay? Well, it's n minus 1. And for each time the outer loop runs, the inner loop runs, you know, some number of times. Let me see, I'm gonna, I hate to get into the math. I gotta tell you, I just hate the math stuff. explaining it is hard. That's the problem. It's easy to explain programming, but when it gets to math, it's tough to explain it. I'm going to give you what I'm leading up to there. It's n squared. So the slow algorithm, the one we looked at, the time is proportional. The time the algorithm to complete is proportional to the number of elements in the array squared. There's some constant times n squared. Just roughly, if you look at it, when the outer loop runs, the inner loop runs, n minus 1 times. And then I advances 1, and the inner loop then runs n minus 2 times. Then I advances 1, and then the inner loop runs n minus 3 times. And you just keep going until you hit 1. So you look at that, it looks like this if you rearrange them. It looks something like this. It's basically, well, actually, it's you turn it around upside down. If you flip it, it'll look like this: 1 plus 2 plus 3, like that. See that? It goes to n minus 1, but I'm just gonna go n there. It doesn't matter. One more isn't gonna matter. And if you look at this, if you analyze this, you'll see that this expression actually is equal to n, something like this, n times n minus 1. I don't know exactly, divided by 2. Oh, we might be off by 1. Maybe it's n minus 1, times n minus 2. So something like it doesn't really matter. And this thing is bounded by n squared. It's bounded by some constant times n squared. So the time that the algorithm takes as n gets larger, the time is sort of blowing up like a second-degree polynomial. You know what a polynomial looks like? It's what do they call, a hyperbola? Is that what it's called? So the graph, it shoots up. It just starts shooting up very quickly. But this expression here, if you look at the graph, it goes up much more slowly because log n is tiny. So it's almost, linear. But the log n just, it starts getting a little big, Like if n was 1,000,000, and then what's log n? It's like 20, right? Log of 1,000,000 is roughly 20, 2 to the 20. This is log base 2, but it doesn't matter. It can work in base 10. They're all sort of they're equivalent. You can use some kind of base and convert between them. So that's it. In later courses, you look in more detail at the mathematics behind these algorithms and learn how to analyze what are called the running times. So now we're talking about the running time of the sort routine that we looked at and comparing it to the running time of a faster routine. All right, that's it for sorting. Any questions? Yeah.
Are we going to be quizzed on this in the next lab?
Huh?
We're going to be quizzed on this in the next lab, right? Okay.
This week or next week, right?
This week.
Is it next?
Oh, I thought we took the rate already.
Yeah, so, yeah, we're doing arrays, yeah. Well, we have a few minutes left. Did you want to talk about arrays? Questions on arrays? These problems here?
The example ones.
Examples?
Yeah.
Which one do you want to look at?
One of the is for keys.
There's a lot on there, isn't there? Do you get this one? This is okay, right? It's two-dimensional. These are the answers. I wasn't going to give you the answers, I changed my mind, just put them in there. But don't be tempted just to look at the answers. You gotta try to figure them out. Which one do you want to look at?
Number 11.
11? Sorry, my hearing is not that great, so I gotta ask. Let's look at 11. Here. Implement a function that computes the total sum of all values in a two-dimensional array with 100 rows and 100 columns. All right, this is it right here. Did you try to implement that? Because we can look at your code if you have it.
No, I was trying to do it in my head. I just knew I had to have a loop.
Just trying to figure it out?
Yeah.
Like in the quiz, you don't have the benefit of having a computer, right? So it has to be done sort of on paper, the old-fashioned way. So we need to implement this thing. You know, what goes in here? So we need to calculate the sum of all the values in this two-dimensional array and return the result. So you can consider that to be the rows and this to be the columns. Or you could do it the other way around. I think of this as rows, and this is columns. I think that's how it's laid out in memory. There's the first line of elements is the first row, then the second line is then the next list is the second row, and so on. I believe that's how it's laid out in memory. The other way to lay it out is to start with the first column and lay out all the elements that are in across all the rows in that column. So that's the other way, column-wise, I think they call it, versus row-wise. So there's two ways to lay it out in memory. And I think that C++ lays out a two-dimensional array or an n-dimensional array row-wise. I believe. I'm pretty sure. Well, I'm not 100% sure. There are times when you need to know that, but we don't need to know that for what we're doing. So I'm going to use the variable r to represent the rows. But we could use I there. You don't have to use R. I is good too. And the variable C to represent the columns. So for each row, we've got, all of the, we have the items for the 100 columns that come. So we'll have some kind of an accumulator that, when we get to a position at row R column C, we just add it into this accumulator, this variable called sum. So we'll need to declare that and initialize it to 0 as well. We need to do one more thing, though. Anybody catch that? A little detail here. You got to return sum, exactly. Is that all right? Yeah.
Can you explain the plus equals just a little
Yeah, this plus equals. I'll show you an equivalent form for that. It's sum equals sum plus ARC. This is the same thing as that one. See, sum is a label for a memory location. This memory location is like a bucket, and you put a number in the bucket. So sum can be 3, some could be 3 million. I mean, sum is like a container of a value. That's one mental abstraction that you can use. There's others. You can also say, well, it's a string of bytes, and these bytes have states. But anyway, let's just go with the bucket analogy. The sum is like a bucket, and you put a number in it, right? So here, when I go sum plus ARC, I'm taking the number out of the bucket, the sum bucket. I'm taking the number out of the sum bucket, holding it in air, well, in a register in the CPU, and adding it to the value that I take out of ARC. I don't modify the value at ARC. I don't modify the value at sum. These are two labels. These are two names of memory locations where there's an integer stored. So I take the value out of both those locations, both of those buckets. I pull them out of their buckets, add them together in air, and then turn around and put it in the sum bucket, killing off whatever's in there. So I overwrite the number that's already in sum, overwrite it with a new value. So this is just a short for that. This says, hey, look at the value that's inside of sum. I want you to increase that value by ARC. That's what plus equals means. So it's essentially the same thing. And it's the same operation in the CPU. It does exactly the same thing. It copies the values from RAM, puts them into two registers, passes through the arithmetic logic unit. The sum is computed, and then the value is produced in a register. Or maybe it's written directly into RAM again. I don't know. It's been a while since I studied computer architecture or organization. So that's it. That's how that works. Anything else?
So when we were sorting an array, we're just using a void function. Is there any way of doing that, like with a reference function, like you know what I mean, like just?
This is a reference. When you have an array,
it's always a.
Yeah, actually, this A here is a pointer.
Okay.
So A is a variable that holds the address of the array in memory. So it's actually it's a pointer.
Okay, so you're not copying A anytime you use a function that takes an array as a parameter?
Yeah, this function, you're making a copy of the pointer value. So, in a 64-bit machine, it's 8 bytes. You're copying 8 bytes that contains the byte address of the first element of the array. And then all the elements that are in the array are laid out sequentially, one after another. So in a reference and a pointer, they're roughly the same thing. Reference and a pointer. Now we haven't really talked about pointers, although it was in the reading material. And you eventually have to learn about pointers. A pointer is simply the byte address of some number. The byte address of some data. in RAM. You got 8 gigabytes of RAM, right, in your computer. And each byte has an address. The first byte is at position 0. The second byte is at position 1, and so on. So each of these bytes is sort of numbered. And A contains a number that represents one of the bytes in RAM. So that's called a pointer. So when we pass in A, we're actually making a copy of the pointer. So if we modify A in here, we can modify A. Just give it a number. That's probably going to crash the program, but we could give it another number. We could say A equals A plus 4. That's modifying A, and now when we operate on A here, it's going to be off by 4 integers. But the A in the calling program, right here, this A doesn't get modified because the pointer variable, the copy was made of the pointer, see? So we can modify this variable A here, which is separate from this. It's a separate memory location than the memory location of the A here that we created inside main. So we're copying the pointer value, just a mere 8 bytes. We're not copying the entire array. So if we go into here, here we're modifying A. Well, actually, when we're swapping, we're modifying A, the sequence of integers that are in memory. So we're modifying the sequence. We're modifying what the data that A points to here. But the variable that represents the pointer to the data, that's the thing that comes in as a copy that we can modify without harming the pointer that's used in the calling code. Is that kind of okay? This stuff is really good to think through all the time, and then you got to get clear on how things are working. That helps quite a bit. And as you go through this, it'll get more and more clear. You start looking at assembly language and computer organization, how the CPU works, how RAM works, then it starts to get even more clear. Okay. Anything else? Yeah, back there.
Number 10 is lucky.
Number 10?
Yeah.
This one right there, sevens?
Yeah.
Oh, well, that's the answer. 10 is lucky. Now, this function returns true if A is a lucky array. What is a lucky array? It's an array that contains at least one 7 and no 13s.
One below, that's 9.
What's that? Oh, that's 9. I'm sorry. 10. Oh, this is a different definition of lucky, okay? So we're playing with the definition of lucky. Here, in this case, we want to have more 7s than 13s. Then it's lucky. So let's look at the code for determining that. All right, so does A contain more 7s than 13s? Well, we're going to need to look at every value in A. Let's just go ahead and put that in there. Put this loop in here. let's look at every value in A. If we find a 7, well, we're going to have a counter to count the number of 7s. And if we find a 13 at I, then we'll have a counter that counts the number of 13s. So we're going to need to declare those counters. And initialize them to 0. And at the very end, we have to decide, well, are there more 7s than 13s? So I'm going to return 7s greater than 13. See, in my mind, I could do it like that, because I do this all the time. So that's how I do it. But you might do it like this. If 7s is greater than 13s, then, return true, it's lucky. Else, we're going to return false, it's not lucky, okay? But that's the same as this one line right here. See, if this expression is true, then return true. And if that expression is false, then return false. Well, let's just return that expression. You see? Let's just return what that expression evaluates to. So you don't have to have all that verbiage to parse through. Just keep it like this. This is how you would normally see it. What you can do it like this if this is easier for you to think about. That's acceptable. Basically, you're keeping track of how many times each of these values appears. So you need counters. You need variables to increment whenever you discover another 7 or another 13. Anything else? This is today's test, right? Yeah. All right, so we're getting ready for this. Good. I think that's it for today. All right, that's good.